Okay, we'll start from current slide. And before we get started on that, while the light is coming on our projector, which I hope it will one of these days, we go over again. Don't know of any other major announcements, but here's one. Next week, of course, is Cougar Connection Week, and Matthew and Dimitri announced this last time, but I just wanted to emphasize what's happening Monday and Tuesday before we meet again. Okay, and then we'll talk about this class. So Monday on the Birmingham campus, starting at 8 in the morning until 1, outside the library. Is that under the covered area or out in the grassy area or where? Outside the library. Somewhere there, okay. Where you say outside the library?
Yeah, outside the library, both campuses.
Okay, I know, but is it in the covered area? Is it in the inside of the quad, or is it out in the grass?
On this campus?
No, I know where it is on the Birmingham campus.
Birmingham campus, I can't be so sure, like I never attended a Cougar Week event at Birmingham before, other than the inductions.
Right. So I bet you it's going to be in that covered area. You'll see the people. You'll see the people. The tables will be set up. It's get on board, volunteer, pair. The outside location just outside the library from 8 to 1. Here are some of the organizations that may be there at the volunteer tables. Big Brother, Big Sister, Ben Green Housing Authority, Bessemer Recreational Center, Faith Chapel, Girls Incorporated, Grace House, Hands on Birmingham, Humane Society, Metro Changers, Oaks on Parkwood, Powership Network, and the Red Cross. Now, have they decided on the blood drive? Is that going to happen or not?
Blood drive is happening the week after.
The week after. Okay, so that'll be the week after. All right. Also, there'll be probably tables set up for campus organizations that you can be a part of. Those are all volunteer places. Ambassadors, athletics, fine arts, honors college, PBL, Phi Beta Lambda, Scholars Bowl, Student Government Association, speech and debate, student support services, and STEM, that's science, technology, engineering, and math. And, I don't know if they have a table, but they should, the math team, the prime examples. I don't think they signed up, but hopefully they'll get the word out too. So that's going to be Monday from 8 to 1, Birmingham West Campus near the library, just outside the library. On this campus, it will be the Constitution Day. Is that going to be a presentation or do you know? Who knows? Okay. But it's 12 to 1 down in the faculty staff dining room, just next to the cafeteria. Then on Tuesday, they just flip-flop. Okay? Tuesday from 8 to 1 on this campus, we'll have the Get On Board Volunteer Fair. I imagine most of those, if not all the organizations, will be here also. And they will, and the on-campus organizations too, 8 to 1. And that's probably going to be that little area down there, sort of a courtyard area between the A building and B building, just outside the library. Okay? Down some steps there. Nice little gathering place there. Now, on the Birmingham campus, then it'll be the Constitution Day activities, and that will be in Thelma Catlin Auditorium. And Thelma Catlin is in the library building, but it's not completely obvious where it is. Let me get Ishmael marked here and explain there. Just go to anybody in the library and ask where Thelma Catlin is. It's just around the corner, but it's down a little hallway, not really well advertised. If you see the Ebony Room, you're close. Go down the hallway near the Ebony Room and keep going back that way. You'll find Thelma Catlin.
After you pass the Ebony Computer Lab, the entrance to this is going to be on your right.
On the right, but you have to go down a little hallway.
Miss it.
Yeah.
It's like right next to it.
Yeah, just go down that little hallway. You can't tell you're going. The door will say academic dean's office or something like that. Go in that and then keep going and you're in Thelma Catlin.
Yeah,
Okay.
I mean, there should be signs over there showing you where Thelma Catlin will be.
Good deal. All right, and there's Justin. Okay. Anyone else come in since the call roll? Okay, and that will cover through Tuesday. Tuesday in class or before class, we'll talk about the Wednesday and Thursday activities. Okay, that's campus-wide. Now let's talk about this class. Where are we? Where we're going? Where we're anticipating? That kind of stuff. So, number one, today we're going to continue and I think finish chapter 18 fairly quickly, I believe. We'll probably have some time to get started on chapter 19. But at 3:15, we will stop and have the lab for chapter 18. Now, this lab is a little different from most of the others in that it's actually we're going into a lab and do literally a wet lab. You know, we're going to do hands-on stuff in a laboratory and take some measurements. Okay? That's not going to take too long. The rest of the lab, and it's only 10 points of your 25 points there. Where we get the other 15 points? Questions at the end of the chapter. So this is the only lab that you're going to have to answer some questions at the end of the chapter to fulfill the lab requirement. Because the lab itself is 10 questions long. I mean, that's it, folks. You know, just 10 questions. So the other 15 points will come from questions. So I'll talk about that at lab time. Okay. After that, the last 30 minutes of the day, we will have the test on chapter 17, the one we finished last time and did the lab last time. So 2 hours of class, 2 hours of lab, 30 minutes of test. I don't think the lab will take you 2 hours. It could. You'll have it if you want it. But when you're finished with the lab, you could take your test and then move on. And we'll talk more about those questions because they are sort of important. Okay. Next. Next week. Next week on Tuesday. Is that, not next week. Okay. And there's.
I think you said the week after.
Yeah, the week after, I know it. And Stephanie is here. Okay. A week from this coming Tuesday is going to be our trip to the planetarium. And that will be, we'll leave here right at 1:15. We don't have much time to dawdle around. So if you're going to be riding with us, be here at 1:15. We'll be getting in the van. Hopefully, I haven't gotten it yet, but I hope to get it Friday or get permission for it on Friday. And then we'll be heading to Sanford. If you're wanting to drive yourself, either going straight to Sanford from home, which is fine, be there by 2 o'clock. If you're leaving from campus here and want to follow me, perfectly fine. But be here by 1:15. Yes. Second. That's a week from Tuesday, the 25th. It's in the planetarium. I have sort of a map. Are any of you at all familiar with Sanford's campus?
Right now.
Okay. Let me explain to you, and I'll do it again as we get closer once I mark DeAndre here. Okay. You know on Lakeshore, and whichever way you're coming from, I'll be coming from the Bessemer side. So we'll be coming in. You know where Wildwood is, where the Sam's and Walmart and lots of other businesses are. Then the expressway, and then we continue on Lakeshore, and Sanford comes up, and there's actually coming from this way, there's two entrances. The first entrance, don't take that one. It's the second entrance. The big entrance has a light there. It has two gates, and you know the out gate is first, and then the in gate is over there. Go to the big entrance there, and go in the in gate. Okay, you'll be going up a hill toward a big building at the top that I thought was the administration building, but I believe it's the library or something like that. But it's a big building. You see it, beautiful campus. But about halfway up the hill, you'll get I don't remember if it's a stop sign now or not. One time it was, one time it wasn't. I don't know what they have. But anyway, the first intersection you come to after you enter the gate, that's an unusual name. Let me find that. I thought it was just on the tip of my tongue, and now I swallowed it. Okay. Here we go, getting close. Getting close. Goodness gracious, the stack is. Y'all need to be getting your papers in so I can get them back to you. Okay, here it is. Here's the campus. Here. On Lakeshore down here, there is an entrance here, and it's called Montague Alley. Don't take that one. Go to the main entrance here, and you see you can enter on this side, you exit on the other side, the big wraparound. That is the library, University Library, that's at the top of the hill. Don't go up there. Go to that first road, and that's Montague Drive. Montague Drive. Take a right, and it has a very gradual right until you've made basically a 90-degree turn, but it's so gradual you don't realize you're turning that much. And there'll be a stop sign here where they have pedestrian crossing. That's about all it's for. The second stop sign there is a second pedestrian crossing. That's where the planetarium is. Okay? But you'll need to park. There is a little parking lot down the hill. This is the big circular drive around here. Down the hill you'll see from there. At the time we go, the odds are that lot's going to be mostly full. If you see a place, it's perfectly fine to park there. Okay? But I would look down there before I turn down there and waste the time and effort driving down there. If there's not something obvious there, keep going up Montague, and it's going up a hill here, and then you'll see a parking deck here. Now, the parking deck is not that easy to see, but it's on the right, and you will see a little lot visible, and then there's a deck. It's only two, lower level and upper level. The little lot is right here. If you see something there, park in it. The deck is here. Usually you can find something there. If you can't, I think you have to get back on the road and go up here to get on the upper level. I don't think there's a way to the upper level from the first drive. You go to the second drive. But in one of those, either this one, the outside, the inside, or the upper, you should be able to. We've always found parking in one of those four places. Okay? So that's how you get there. And it's not a building per se. I mean, the Crescentberry Planetarium is in a building, and they don't really have these labeled too well. When you're coming up here around the bend, you'll see it's a greenhouse type building here. They call it a conservatory. Okay? And then there's a big, long classroom or building of some nature here, and Crescentberry Planetarium is at the end of that up toward the road. So when you walk in there, there's a little sign that says Crescentberry Planetarium, but you have to be very watchful to see it, okay? And that's where you go in, and either one of the first two doors to the left, once you go down about 3 or 4 steps, that will be where you go. And if you come with us or follow me, we'll all get there together. If you're not there, I'm going to try to get there early, and I'll be standing outside for probably 10 or 15 minutes after he gets started, or before he gets started maybe, but out there visible. So if you do drive by, you'll see me, and then I'll let you know where we parked and where you probably can get parked. Yes?
Private van is free, right?
Yeah. If I can get the van, which I think I can this far in advance, yeah, it's free. It's the campus. It's the van. I can't remember how many it will hold. I think it's classified a 15-seater, but I don't think the insurance will allow us to do more than like 11 or 12, just insurance purposes. Okay, yeah, he's going to present starting around 2-ish or so, because we leave here at 1:15. It'll take us pretty close to 45 minutes to get there. And we'll start around 2. He'll go till about 3:30, Then we'll get in the van in your cars or whatever and head back here. We should be back here 4:15. We have another hour and a half. So we will have class afterwards, whatever would normally have been scheduled. I can't see that far in advance. But whatever we're working on, we'll continue working. Won't be time for a lab. There would be time for a test if that was called for, and certainly would be time to have a little bit of lecture before whatever comes next. Do y'all want a copy of this? I can make copies if you want it. How many want copies? 1, 2, 3, 4, 5, 6, 7. 70 copies. I'll try to remember to get about, I may go on and make 10 just in case. Okay. And we will head that way on a week from Tuesday. Okay. All right. Any other questions concerning physical science or scheduling, planning, whatever? All right. Last time we got up to, I'll show the last slide, lithosphere, plates, and boundaries. Okay? The basis for plate tectonics. We did this slide. They mentioned 3 plate motions at the very bottom, divergent, convergent, and transform boundaries. Starting now, we will hit each of those individually. Now, here was the map of those that we saw at the very beginning, a little bit better picture of those various plates on the surface of the Earth. Okay? You already had this slide. Okay. So let's start with the divergent boundaries. This is as opposed to the divergent, the book and movie that they had, but this is different. The divergent boundaries occur between 2 plates that are moving away from each other. Okay? Plates that are separating from each other. If this is happening, the 2 plates are moving apart, they're resting on this semi-liquid material. If they move apart, the pressure is going to force it up. And that's typically what happens. Molten material from the mantle rises to fill the fissure when they split, when they separate. Therefore, you've got new crust being formed because that molten material is going to come up. Most of the time, this is underwater. Okay? These plate boundaries are generally underwater, and when they split like that, the molten material comes up, they harden real quickly because of the water, and makes new basaltic rock, or glassy volcanic rock if it doesn't have time to crystallize properly. So that's new crust is formed, often accompanied with volcanic activity. Some of these volcanoes are below water and you never see them. You can sense their heat and it's that kind of stuff. But some of them, like the island of Iceland, yeah, that's why they have periodic volcanic eruptions, because they're in that divergent boundary. And the Mid-Atlantic Ridge is the prime example of that, okay? Let me go back to that slide, and here's, it doesn't show up really well here, but here's the Mid-Atlantic Ridge. There's Iceland right up there, right on that ridge, and this is that divergent boundary going right down in between South America and Africa, about halfway there, halfway between Europe and the U.S., halfway just about all the way up, and that's the classic divergent boundary. There are others, and you'll see and talk about that in the last chapter on the oceans. You will do a lab and you'll look at some of the ridges and trenches. The ridges are usually where these boundaries are, okay? Divergent boundaries. That's the classic Mid-Atlantic Ridge. Okay. So, here is an illustration of sort of what's going on here. You have, for some reason, we're not getting into the reasons yet, we'll do this right at the end of the chapter, the plates are splitting apart, diverging, moving apart. Well, the magma that's under here in the asthenosphere, remember, this is the oceans on top, There's the oceanic crust is here. That's the part of the Earth's crust. The oceanic crust is there. Then you have the upper part of the magma. That's here, and the upper part of the magma and the crust are called the lithosphere. Well, everything splits there. New magma comes out. This is the asthenosphere here. Now, they haven't drawn this to scale. These are much thicker than this. This looks like this is a huge thing. These are bigger, but they're just showing. The magma then makes its way up because of all the pressure here. It forces the magma up, and you have this bubbling over the top here. Now, sometimes it hardens in the crack, and nothing happens for a few years or decades or something. But at some point, it's going to continue diverging, and then a new fissure would happen. So this is what's happening with the divergent boundaries. Kind of make sense? Okay. Now we have convergent boundaries. Okay? This is where two plates, and guess what? The globe is a fixed area, right? Okay? Nowhere, nothing's bulging out or sinking in. It's a fixed area. So if two plates are diverging here, somewhere, those two plates, there must be other plates that are coming together. And those are the convergent boundaries. These occur where two plates move toward each other. Here, the old crust is destroyed in the process. In the divergent boundary, new crust is being formed. In the convergent, you have to be destroying some crust. And we'll talk about how that happens. Now, we'll get to three possibilities in a minute. And this is talking only about two of them, okay? But there is an area called the subduction zone. This is where one crust goes underneath the other. It's being destroyed. They were here. This one, as they converge together, one goes under the other, okay? That's the belt, where one crust subducts or goes under the other. Subducted material, okay? Now get this. If you can imagine a whole part of the crust, and this, by the way, we'll learn over here, is oceanic crust. It's that thinner basaltic crust. It goes underneath either another oceanic crust or a continental crust, one or the other. As it does, it's not a pretty sight. They don't want to move past each other. They don't want to go under. And there's a lot of rubbing. There's a lot of friction. There's a lot of obstacle in the way that's not smooth. None of these are nice, smooth, glossy, polished surfaces. They are rough. So they get hung up on each other. There's a lot in the way. So part of that, and you're getting down into the mantle, is getting hotter down there. Some of that subductive material actually melts. Maybe up here, maybe much lower, but somewhere down there it melts and either rehardens as part of the mantle or the melted part goes back into the asthenosphere. One or the other is happening down there. Okay. Now, here's the three possibilities. You could have a continental crust and an oceanic crust. If that's the case, these two are converging, then the continental crust is the one that goes on top, the oceanic crust goes on the bottom. Can you think of a couple reasons why that might be true? That the oceanic crust would go under or subduct under the continental crust. Yes? Because what? Yes, it is. Basalts are more dense than granites, basically. So therefore, they're going to go under.
Isn't the continental crust like hard too?
Yes, it's a continent, and the oceanic is down here. So yeah, that would make sense for that to happen too. Now the problem is the continental crust is usually thicker as well, so the oceanic crust may have further to go to subduct under it. But it's not going to be a pretty sight, like I said before. You're going to have all sorts of resistance and problems happening when that happens. Now, the second of these is converging oceanic and oceanic crust. And there's no real obvious reason why one does the other, but one goes on top and one goes on the bottom. So one does subduct under the other. But when that happens, and it also happens in the subduction of the oceanic crust under the continental, you get trenches there. This is what I was talking about before. In chapter 24, we'll talk about these ocean trenches and ocean ridges. The ridges are from diverging crust pretty much, and the trenches are from converging crust when one is subducting under the other. The deepest part of the ocean is one of these convergent oceanic plate trenches. That's the Marianas Trench. We'll talk about that in a later chapter. And then the third of these. And there again, you're losing, this is where you're losing the crust, because when it subducts under the other, ultimately it's going to melt. You know, it's going to join the mantle. It's no longer part of the crust. Okay, here's the third one. This is when a continental crust crashes into, it's not like that, but converges with another continental crust. Uh-oh, SpaghettiOs. Where is it going to go? Those don't really subduct very well, do they? They go up. Say again? Make mountains. You got it right. And if you think about, let's go back here. Here is one of those continental converging zones. North of India, because this is the Indo-Australian plate here, India-Australian plate here. Now some of this is oceanic, but parts of it are continental. Okay? And up here, you have a converging boundary between the India-Australia plate bumping into the Eurasian plate. Okay? And does anyone know what's up there, north of India? Say again? What mountains? The Himalayas are there. The tallest mountains in the world, and still growing, because it's still happening. There are some of the newer mountains too, geologically, because this hasn't always been the case. But the Himalayas, the tallest, I think the 5 tallest peaks in the world are all in that region of the Himalayas. I mean, they're up there. Okay, and what's more, the whole area is raised. I mean, Mount Everest is the tallest mountain on the planet, but it's already on a really high area because this whole place is actually being lifted, uplifted, they call it. Okay, so that's just one example of that. You also have right here, you have a plate coming into the North American plate in some senses, and down here you see all along here you have this happening, and the Andes Mountains are still growing because of this. There's a couple of reasons there. But these are oceanic, sorry. This is continental, and they are growing. Now, also inland, you still find these pressures happening, and our Rocky Mountains are still growing. They're way inland. They're not on a plate boundary, but the pressure is forcing them up. The Tetons, right near Jackson Hole, Wyoming, and fairly close to Yellowstone Park, they're still growing. You can't notice or measure, but over long periods of time, they do notice they are still growing. Certainly the Andes are too. We'll talk about that later. This is the continental crust area. Okay. Now, those are converging continental plates. All right, so let's talk about each one of those. I'm sorry, I forgot they had these slides too. We'll do more on this, okay? The oceanic continental plate convergence. So I mentioned South Pacific plate against the South American plate. The Andes are growing there. Okay, oceanic plate is a denser basaltic material subducted under the less dense granite-type continental shelf. So that's what's happening here. And you always have a trench there. I think I mentioned before, when I was in the Navy and we would exit San Francisco Bay and go out into the Pacific, you could just, if they did soundings or things like this, and ships that had sonar could do it off the bottom and stuff, and the bottom would just be going down, down, and get really deep, but then it would start coming back up again, because that was that trench where the oceanic crust subducted under the continental shelf. Okay? These are marked by oceanic trench, deep-seated earthquakes. And where do we have the earthquakes? California, Chile, all these places where you have these boundaries going on. You're absolutely right. And volcanic mountains. And if you look along, let me get the globe, Robert. Let me go back to that. Now, let me get the globe. What is the area around the Pacific Ocean called? The Ring of Fire.
That's what I was talking about.
Yeah, okay, right. And that's Johnny Cash sang about it, right? No, okay. Oh, someone knows Johnny Cash. Okay. All along here you have, because in the Atlantic there's spread, so in the Pacific there has to be contraction. So in South America down here, look just inside that boundary. Look at this mountain range. My word, the Andes Mountains are right there. Now, most of that is because of volcanic activity. Deep-seated earthquakes create fusion, fissures, and that's where the magma comes up. So that's happening there. But you come on up, all along the Pacific. This is a nice globe because it does have the raised areas. And you can feel, they're not as tall of mountains, but there are mountains all along there. And we know it is here. There's the Cascade Mountains up here, where there's the pressure, and that includes, what's the one right outside? Lanier. No. There's Mount St. Helens, Mount Rainier. There's all these Cascade Mountains right up there. They don't list all of them here, but there's several of them. Shasta, Baker, I don't see it on here, but I know that it's up there too. So there's a whole bunch of mountains, and they're basically volcanic mountains because of this. Deep-seated earthquake underneath the continental crust, way down there, the fissures happen because, like I said, it's not a smooth transition. Okay? And this is exactly the one I was mentioning. Convergence of the South American plate with the Nazca plate, and that's what has this huge mountain range, the Andes. The Andes typically are much taller than our Sierra Nevadas or even our Rockies. Okay, the Andes are huge, and the countries along those. This is Peru, Chile, I guess it is, into Argentina and Bolivia. They sort of peter out around Ecuador, but Ecuador is still raised, but not as much as the mountains. And I guess a northern branch of them comes on up into Colombia. But there is the convergence of the the Nazca plate, which is the oceanic plate, it's subducting under the South American plate, which is continental, of course. Okay. Here's an illustration of what's happening there. The oceanic crust and upper part of the mantle is being forced down underneath the big continental crust here. And as it does, I mean, there is friction here, folks. Lots and lots of friction. It's not an easy, smooth transition. It gets hung up on rocks, boulders, whatever. It gets in place, but this force is still there, pushing farther. And suddenly one will give way. Deep-seated earthquakes. That is exactly what causes those earthquakes. And there's so much friction, it may be deep enough here, really getting close to the, not real close, but somewhat to the outer core, which is all molten material. So that's hot there to begin with, and you get the friction here. That's enough to melt the crust, either the continental crust or the oceanic crust. And as it does, if that friction and stuff and giving way of the earthquake creates fissures here, there's some that can go all the way to the surface and create a volcanic mountain. Now, just recently, Japan had another fairly major earthquake on Hokkaido or something like that. It's a northern island of Japan, not as densely populated as find Japan. So there we go. There's Japan. I don't think they listed on this. There, yeah, here's Hokkaido, the northern mountain. This is Honshu. I was thinking it was Honshu, but that didn't sound Japanese enough. Honshu is the major island that where Osaka and Tokyo and all those are. The northern big island is Hokkaido. That's where they had the volcano. And I'm pretty sure that's where they also had the earlier one that caught Fukushima, was the nuclear plant that erupted because of that. All right. Make sense? Notice the continental lithosphere stays up. This is continental crust. This is oceanic crust. They say lithosphere. Well, maybe they mean that, but this one then would be the mantle. They don't label it that way, but you get the general idea. I would have called those crust and this mantle. I think that's probably more accurate. This would be mantle, so this would all be oceanic lithosphere and continental lithosphere. It counts the upper part of the mantle because you don't see the asthenosphere, so that still has to be mantle. Okay, any questions? All right, so let's go now to ocean-ocean plate convergence, the middle of those. Okay, you don't really see it because it's all happening underwater, usually deeply, deeply underwater. The trench in the underwater ridge is created by subduction, okay? Now they indicate an underwater ridge too. The trench is the major component, but you see above the trench, you're forcing up a plate too, and that creates sort of a ridge, especially if it has volcanic activity around it, then it makes even more of a ridge. Associated with deep-seated volcanoes, again, most of them underneath the surface. However, places like the Hawaiian Islands are volcanic islands. So whole islands are made of volcanoes. And remember, Kilauea, back during the summer, was going off almost continually, and they had lava flows that were just heading toward towns, heading toward farms. There's no way to stop them. I mean, they just, you have to go. They did slow down after a while and back to being normal. But Kilauea is just always erupting a little bit, but it was really got carried away this summer. Okay, deep-seated volcanoes. The island arcs form where melted, subducted material rises up above sea level through the overriding plate. So the ridge actually comes all the way up. And if you look, Japan is an arc island. You see the arc in it? That's because this plate, that's what's created. And that's why they still have earthquakes on the seaward side there, because it's still happening. It's constantly happening. The oceanic plate is subducting underneath this plate, which probably was an oceanic plate too. Here's the Aleutian Islands, arc island chain, happening there. Here's the peninsula and islands coming off of Russia, an island chain. It just continues into Japan. They just have a boundary there. You go on down. Basically, remember the India-Australian plate was here, and this is Pacific plate here, or Filipino plate here. Well, look at this. The whole nation of Indonesia is an arc island. Big islands, big arc too. Over here, New Zealand, arc islands. Okay? Over here you have the Melanesia, arc islands. Here we have the Micronesia, arc islands. I mean, they're just all over the Pacific, these arc islands. And the Hawaiian Islands are, and then some of the islands north of them are not all at plate-plate convergence, oceanic plate convergence, but they're either weaknesses in the plate or something like that. But these big ones are where that happens. And one of the examples, prime examples, is the whole nation of Japan, probably with some stuff above and below. And the Philippines, they're right at the edge of the Philippine plate. They don't make as pretty of an arc, but they are there where the convergence happens. There's another set over here. I've got to find them. Yeah, Marianas Islands. Look at that arc. And this is where that deepest trench in the ocean is. The Marianas Trench is somewhere right in there. They don't list it on here. So anyway, they're there. All right. Oceanic plate conversion. Okay. Almost looks like the last picture, but it's not a continental plate on the side. It's an oceanic plate. So here the oceanic plate is abducted under another oceanic plate, and again the friction, and the closer it's getting down into the hotter part of the mantle, then some of this actually starts melting. If it creates fissures from the earthquakes that happen, they make their way up. And see, underwater, you don't see them. Underwater is all sorts of little islands like this, but you don't see those because they're underwater, but they're volcanic islands. But this one, that one have actually grown big enough, they break the surface. And that makes your island arc. If you continued on up there, somewhere it's going to bend that way or bend this way or something. Those are the arc islands, created by the deep-seated earthquakes making their way through the upper part of the oceanic crust. Does that make sense? Okay, in Japan, Hawaiian Islands, Aleutian Islands, New Zealand, Marianas, all those are these arc islands. Okay, finally the continental plate convergence, we've talked about that. The less dense granite materials resist subduction. They're too big and thick. They're not going to go under, so they just sort of very slowly crash into each other. And then there's nowhere to go but up. Okay? Colliding plates pile up, producing a deformed and thicker crust of lighter materials. And here the clear example of that is the Tibetan Plateau, which is the whole area called Tibet, has been raised up there, and the Himalaya Mountains are the classic, what is they call it, the obvious results of the continental plate conversions. India, Australian plate conversion, that's continental plate on the India side with the continental plate, Eurasian plate. Nowhere to go but up, and there they went. Now, if you remember, when I was mentioning, when my wife and I were traveling in, I'm trying to remember which it was. These are the Rocky Mountains down here. And we were sort of on the eastern side of the Rockies, I think, or right in the Rockies, and we were seeing basalts, which is supposed to be the oceanic crust, okay? What were they doing there? Well, over time, this has been uplifted. Over a long period of time, this has been uplifted, and that's why the Rocky Mountains are there, because of that pressure when that was happening, okay? And that's why things that were at the bottom of the ocean, I mean, millennia ago, are now up at high elevations because they've been pushed upward, okay? Here's the picture that accompanies continental lithosphere here, continental lithosphere here. Think of India, Australian plate here, the Eurasian plate here. They come together and just materials are forced up. Now, in the next chapter, we're going to be talking about how these kinds of pressures will then create arcs, create other things going on in here, bending layers, and forcing things up. Okay, so there's continental plate convergence. The third kind, wait, sorry. Okay. So who knows, maybe where the Rocky Mountains are now, maybe there was another continent that got pushed into the North American plate, and that's what formed the Rockies. I don't know, this is just speculation. And they sort of are joined together now and all called the North American plate. Who knows? Maybe it was different, because right along that we find the Great Salt Lake in Utah. What is a salt lake doing way out in the middle of the desert there? Not desert, but mountains there. Where did all that salt come from? People think it perhaps was once a marine environment, part of the ocean. And it got uplifted, but the lake continued to hold water. Everybody got it? Okay. The third kind of boundaries, we have divergent boundaries, the plates moving apart, converging boundaries, the plates moving together, and then we have transform boundaries when the two plates, and I don't like this verb here, they don't slide, they grind past each other. That's not a smooth transition at all. But when they do move past each other, okay? The crust is neither created nor destroyed in the process, but it causes a lot of friction, and the irregularities in those movements along the boundaries are what we call earthquakes, okay? If the pressure is there for them to be sliding past or moving past each other, but they get hung up on some rock that's sticking out there, boulders, who knows what, and get stuck up, but then the pressure continues to increase until it suddenly releases. That's what creates the irregularities in the movement, those sudden jerks, and we're not talking about the people. No, okay. They produce the earthquakes. Okay. And one of the classic examples is the San Andreas Fault along California's coastline. And let me just sort of point it out to you here. I don't know, you probably can't see from here, but it goes pretty close to the coast here. But when you have these Cascades and the Sierra Nevada mountains here, yeah, they're not far from being where that San Andreas Fault is. Right there. San Francisco Bay. They don't show it well here, but you can really, if you look at a map, you see it cuts in on, it's just about right on that San Andreas Fault, okay? And it goes on down, and it goes inland a little way, and I've never seen the continuous map of it. My guess, though, this Gulf of California, here's the Baja Peninsula in Mexico, just barely a little bit of land across the top of that. I think that's sitting right on that San Andreas Fault, okay? I think that Gulf of California almost defines the fault down there. And that's rather bizarre and a unique representation of a fault line. But that's the transform boundary, sliding past, or not sliding, moving past each other, grinding past each other, giving way to sudden jerks, which produce earthquakes. And that's why San Francisco, Los Angeles, all those areas have had so many earthquakes over time. The major one in San Francisco was back right around 1900 or so. It was either 10 years before or 10 years after. Major earthquake in San Francisco. They started building for better earthquake resistance then. Then in the World Series, can't remember what year it was, when Oakland, California was playing San Francisco. Oakland Athletic playing the San Francisco Giants. They called that the Bay Bridge World Series. I mean, they just had to drive across the bay to play their games. I mean, you couldn't get much closer than that. One of the games happening, I think, in San Francisco, back then it was called Candlestick Park. I think nowadays it has a new name, 3M or something like that. But anyway, the game was being played there, and you had an earthquake happen, and it was major. I think I told you about across San Francisco Bay there's what they call the Bay Bridge Tunnel. Now, that sounds like a strange combination of words. It's mostly a bridge, but there's an island right in the middle of the bay called Yerba Bueno, which means good herbs, good growthy stuff there. And they tunneled through that mountain, the island, and came out on the other side, with bridge here and bridge there. It was a double-decker bridge. One direction went east and the other direction west. I don't remember which way they went. And the earthquake was bad enough that the upper level crashed down onto the lower level, cars in between there, and it was a busy time. It's always busy. Some of them are absolutely crushed. People killed immediately. Just within 2 or 3 years later, a fairly major earthquake down there in Los Angeles. And there you saw expressways, just dropping down onto the streets beneath them. There were some major, and they were building earthquake-resistant stuff. It wasn't like Haiti where nothing was built according to code. These were built according to code and still had some pretty major disasters happen. Okay. Now, San Andreas isn't the only fault in the U.S. There's another fault line of all places.
Like in Haiti?
Yeah, Haiti had a major earthquake there. Find Haiti, it's right there. It's the western half of, what is that island called? I can't think of it. Hispaniola. Hispaniola is the yellow. That's the island. The western half is not quite half, a little less than half is Haiti. The eastern part is Dominican Republic. And Dominican Republic is pretty much more advanced than Haiti is. Haiti is much more populated, even though it's smaller. And it's Dominican Republic speaks Spanish. Haiti speaks French or Pidgin French. They were different continental. When the empire's colony, they were colonized by different countries. Okay, so they had an earthquake, but the other fault line is really close to the Mississippi River. It's called the New Madrid fault line. Madrid, Missouri, somewhere up in the middle part of the country, and there's a fault line that goes there. And when the last time that had a major earthquake there, and it was major, it was way early in our history. I don't even know if we had much development there. They actually said the Mississippi River ran backwards for a couple of days. It ran upstream because the quake was so major that it forced the water back up and then it came running back down. That's pretty major. If you've seen the Mississippi, that's the other one. But the San Andreas is the most famous. You'll read about the other one in your text. Let me see if I can find that. It may not be this chapter. It may be a later chapter. Let me see. I've also been forgetting to turn pages. Before I get too far off of it, they can measure plate movement, and there are some, there's a little blurb at the top of page 469, really worth your reading, and they talk about some of the astronauts who actually put things on the moon that can measure things going on the Earth. And they have been able to detect plate movements that way too. All right. There are some examples we haven't talked about, earthquake data from subduction zones, and they're talking about distances and things and slopes. And those are fun problems to look at, but it has nothing to do with what we talked about, very little to do with what we talked about. Sort of like they had to make up something to put there. Okay, so those are our transform boundaries. All right. It's in the later chapter we talk about those, but we'll bring up the San Andreas Fault again in the later chapter. All right, what's our present day understanding? Not complete, let's put it that way. The major remaining question, what makes them move? Why aren't they just stable? Why are they moving? What drives the plates? You would think they just bump into each other a little bit and stay where they are. Why do they split? Why do they converge? Why do they diverge? Why does this happen? Well, here's one of the current working hypotheses, okay? Remember the asthenosphere. That's that elastic, semi-liquid, somewhat plastic mess that's in the between the upper part of the mantle and the lower part of the mantle, okay? It's hot fluid materials rise at the diverging boundary. Yeah, we understand that. But what makes them diverge? That's what they haven't answered. But where they are diverging, the hot material comes up, and then that tends to make them diverge more. And maybe that's what's happening, okay? Some escapes to form new crust. The remainder spreads out beneath the lithosphere, dragging the underlying plates with it and making it split more. The problem is very little supporting evidence. And again, why? Why is that happening? Okay? We're not sure. Something had to initiate, and no one's quite figured that out yet. Okay? Here's sort of a picture of that. Now, so the last pictures I thought were labeled sort of poorly. This one's labeled a lot better, but it's such a broad scale that it's hard to see much. But picture this being the middle of the Atlantic Ocean. It doesn't have to be. It could be anywhere you have a diverging plate. But that's the most classic. Over here we have Africa or Europe, you know, here, and where the oceanic plate subducts underneath the continental plate. Now, the scale here is a bit bizarre. Notice all these stars here? These are places where there's been breaks and disruptions and stuff. These could be earthquakes. Later we'll talk about these as shallow-seated earthquakes, medium-seated earthquakes, and deep-seated earthquakes. The deep ones, pretty major, okay? The oceanic crust is being subducted under them. Frankly, I don't think it goes that far. I mean, I think it melts well before that, but the scale is a little off here. But where they are diverging, then the convective cells can come up, the heat rises, and then some of it makes its way through the surface, forming new crust, but others of it don't get through, and then they are moving this way, dragging the plates with them, then making it open up more. Okay? What's the initiator there? We don't know. Well, over here, and this would be in the Pacific now, and it happens in the Atlantic too, oceanic plate conversion, this one being forced under this one, and you have these earthquakes, shallow-seated, medium-seated, and deep-seated earthquakes. These form those arc islands, island arcs, you know, where here's your underwater trench, oceanic trench, here's your oceanic continental trench that's just outside there. Okay? You have the rift. It seems sort of crazy. They say Rift Valley, rift meaning raised, but valley meaning low. But you have that in here, Mid-Atlantic Ridge in here. That's where the new crust is being formed. And then over here you have the trench where it's being subducted. Now, what's happening to the destroyed crust here? Some of it's coming up as volcanic activity, and it's forming new crust. Okay, so All this is always going on. Now, in an earlier text, earlier edition of this same text, they had a couple of other theories. They had one, the slab drag theory, that since this is moving down, is pulling the trenches apart. You know, and it may be a combination of the two. Who knows? Our understanding is pretty minuscule. At least we know it's happening now. Back in the past, they didn't even think that was possible. Now we think it is. Okay. I think that may be the last slide, and it is. Yes. Oh, yeah. I'm sorry. Okay. Under the myths, mistakes, and misunderstanding, I think someone's already asked about this a few weeks ago. Is it true that California is going to break off and fall into the ocean? No. That is the fault line there is a transform boundary. It's just moving past each other. It's not breaking. And by the way, this whole concept of an earthquake, the earth opening up and people from things falling in, that's Hollywood. That's not real. The only places you have those diverging boundaries are the bottom of the ocean pretty much, and nothing's falling in. Magma's coming out, you know. So, yeah, that idea of an earthquake, totally wrong. Now, in a later chapter, we'll see an example along the San Andreas Fault of a field that's been planted. It's big agricultural areas. A field that was planted, then the earthquake happens, and the roads don't line up anymore. You know, roads were coming in like this. Now they're like that. You know, you can tell there was a shift, transform boundary, a movement past each other so that they don't line up anymore. And it was several inches. Obvious, you know, right there, because the farmer couldn't have done that, you know, with his equipment. That happened because of the earthquake. You'll see that in a later chapter. So, lots of theories, unfortunately, very little supported evidence. And then, what starts them moving anyway? Why would they be moving like that? But they do. And maybe it's the spin of the earth is enough to create some of this. I don't know. I really, I can't even imagine. Okay? But this up here is a really big thing. The core here, the hot material leaving the core, going up, cooling at the top, coming out. This is the example of convection. Hot rising, cool dropping. And that would be pulling the plates with it. But there's not much evidence. Nobody can go down there and test, you know. It's just way too deep, way too hard, way too hot, way too everything. All right, everybody got it? So that's the last slide. Before we leave, the myths, mistakes, and misunderstanding, bye-bye California. It is a myth that will eventually fall into the ocean. Not going to happen. It's a transform boundary, not a divergent boundary. So that's not going to happen. Here's here's how they end that little blurb. I don't know. It's been a long time since I read it. I'd forgotten this. However, some 15 million years ago, million years and millions of earthquakes from now, Los Angeles might have been across the bay from San Francisco. So that is a really bizarre thought that possibly that much motion has occurred over millions and millions of years. I think that's pretty much exaggeration. I don't think it would have been Los Angeles. Maybe San Jose, but not Los Angeles. Okay. I don't know. May have. Nobody was there to write it down. Okay. And I think you'll know the next. Oh, yeah. Wait. Let's wait. The person behind the science this time, Harry Hammond Hess. Nice and alliterative name. He was a naval officer, mostly in research positions, U.S. geologist. Played a key part in the plate tectonic revolution of the 1960s. He did a lot of the very, very, very careful measurements that showed and illustrated that the plates are really moving. Okay, so it's well worth a read there. If you choose to write on him, know that this is not your source. You have to go outside the book to get your source. It does mention a few other. Maurice Ewing's discovery of global distribution of mid-oceanic ridges. So he would be another person you could write on. There's also D.H. Matthews is mentioned, his student F.J. Vine. They did a lot of the work on the magnetic anomalies in the sea floor and how they are tied together. Okay? Oh yeah. This one's not on the slide, but it is still in the text. Okay? This one goes along sort of with that one here. Here's a ridge. They call this the ridge push. The weight of this is pushing this downward. The other way to think of it is the downward part here is pulling the ridge. Maybe a combination, we don't know. Okay? But those are a couple of other illustrations that follow up on that one and some of the earlier ones you saw. Then there's a science and society, geothermal energy. Okay? And I think I've already mentioned to you Iceland, and they don't even mention that here, they only talk about the U.S. Iceland is just about totally heated with geothermal energy. They don't burn that much fuel, they don't have that much electricity, they use geothermal to warm their homes, and they are way up there. Iceland is the name of the country, they're cold, but they use geothermal heat, hot water off the volcanic rock to warm, provide the heat for their homes. So, nice thing here, but they're talking mostly about the U.S. The Juan de Fuca is the plate subducted beneath the continental lithosphere. Remember, it's about the smallest plate out there, so if it continues for very long, at one point it's probably not going to be there anymore. It'll be completely underneath. Okay, it melts, forming magma, buoyed toward the Earth's surface, erupting volcanoes. It's just a never-ending cycle. Also, geothermal resources in Hawaii, of course. One use of geothermal energy is to generate electricity. You can read that. Geothermal power plants are located in California, 10 sites, Hawaii, Nevada, 10 sites, Oregon and Utah, 2 sites each, or maybe 2 sites in Utah. Those sites have a total generating, and you can read more about it. Really a good way to go, because guess what? That's clean energy. I mean, it's all coming from the earth itself. So there's some questions to discuss once you've read that. If that gives you ideas for paper topics, go for it. Okay. And over here on page 473, even though they show the ridge push, but over in the right-hand column they have the slab pull. That was the other one. I knew the earlier editions had it, but I couldn't remember if this one had it. Okay. Oh, and here's the figure for slab pull. It's fairly similar to this one. The ridge is here, and here's where this ducks down, but they have it going up, and this is dragging that opening up the ridge. Who knows? It could be the convective cells, it could be the ridge push, it could be the slab pull. New thing, concepts applied on new earthquakes and volcanoes. You might want to check that out. Okay. I started to say this earlier, but I'll say it again. Nothing replaces reading the chapter. Maybe more than once, maybe several times. Good way to study. The summary at the end is one of the shorter summaries, not as long as some have been, but it has a lot of the keywords in it in italics. Then again, the key terms are listed underneath it, and again, probably a little bit shorter list than most chapters have. And then applying the concepts, all multiple choice questions, and whereas other things are shorter, 52 questions here. That's more than most. Well worth your time to spend doing those. Okay? Questions for thought, and we're going to get to these later. 16 questions there, 4 for further analysis. And hang on to these, because part of today's lab is going to be answering some of those questions. Okay? We'll talk about that a little bit later. There's a little invitation to an inquiry about how to measure plate motion. If you're interested in that, you can read that. The parallel exercises are mostly the quantitative ones that they kind of just make up to fit them into the text here. You decide whether you want to do those or not. All right, any questions? I don't have my watch out. How are we doing time-wise?
2:34.
To what? 34? Okay. So we're going to go till 3:15. So we got plenty of time to get started on chapter 19. Any questions on 18? Okay. Now let's look ahead in our crystal ball again. You know, about however many minutes, I said 20, 25 minutes to go. We'll be introducing chapter 19. Then we'll do the lab on 18. So it's sort of covers all the chapters we're doing now. But we will answer some questions in 18. Then we'll have the test from 17, the one we finished last time. So let's look ahead. Tuesday of next week, we will more than likely come close to finishing chapter 19. So good chance we'll do the lab for 19. And then we'll have the test for 18, for sure. Whether we finish 19 or not, we will be doing the test on 18. So it's moving along, folks, pretty rapidly. Some point we'll probably have a day that we either don't have a test or don't have a lab, or have one or the other or whatever. But right now we're kind of grinding along and having a test and lab. See, last time we just had a test with no lab. This time we have a lab and a test. Next time, more than likely a lab and a test, and probably after that will be one without the other. Okay. Any questions on anything in 18? So let's end 18 and go to 19. And then 19, even though it has a new title and stuff, it follows directly from what 18 was doing. It's going to take a while for it to open. Here it comes. Okay. Let's get it open from current slide. And we will do building the Earth's surface. And this looks like it goes directly with what we were doing before. Now, the picture in your text is a little more recent than this one, but both of them, I'm guessing they were taken on the island of Hawaii. They could have been any other island that have active volcanoes on them, but I'm guessing these probably are Hawaii. They don't say, they don't specify, but where lava is coming up and reaching the surface and hardening. This was formerly lava here, and that's how one way that the Earth's surface is being built. Okay? Now, looking ahead to the next chapter, it's called Shaping the Earth's Surface, which basically is how the Earth's surface is being worn down. So the Earth's surface is being built in this chapter, worn down in the next chapter. Okay? All because of the plate tectonics, pretty much, that we just had in the last chapter. So the core concept here, the surface of the Earth is involved with plate tectonic processes, that was the last chapter, that result in an ongoing buildup of the surface. Okay? But that doesn't mean the surface is just growing. Couldn't do that. It's also wearing away. And that'll be the next chapter when we talk about shaping the Earth's surface. And we'll hit some more of these terms. Remember, We had sort of a star's lifetime cycle from the time that the masses of gases, the nebula, came together, and then became a protostar, became a star, lived the star's main sequence life, then used up all of its fuel, started exploding several different times and stuff, finally blew itself out into space. The gases went back into space, they formed again, and who knows how many times they cycled stars through them. Okay? Same thing here, things cycling through. Here is a picture, I'm pretty sure this is Shasta, Mount Shasta in California. Now the upper part's so high that it's snow covered, but you can see sort of the craters, the more than one probably, and you can see the lava flows here from way, way past eruptions, and probably these are also lava flows here, okay? Just one way that the Earth's surface is being built. Yeah, it's a volcano, but it hasn't been active in any of the time that we've been here on the in the U.S. But it's obviously a volcanic mountain. What we call them are, what do they call them? Not inert, but I guess at one time they called them inert volcanoes, but inactive or something like this. And there was another one fairly close to this one, not super close, but within a few hundred miles, called Mount St. Helens, who had never erupted in the time we had been on the North American continent. But it erupted pretty major back in the 80s or so, and so who knows, any of these others could decide to awaken after long snoozes. Okay. So, how do we interpret the Earth's surface? This is basically the topic 19.1 on page 482. Okay. Here's one of those cyclic type things. The principle of uniformity. And basically, let me back off. I wish I'd have put this together differently. Way back in the past, okay, people thought that the Earth had gone through a series of catastrophic events that made the Earth like it is, and then it stopped. With just little skirmishes here and there, maybe an earthquake every now and then, volcanic activity every now and then. But basically, we were in a quiet stage. Well, they do happen, catastrophic events, but it wasn't just there was one big one, and then, unless you're talking about when we were formed in the planetary nebula, but that's not what you call it, planetary whatever, protostar, protoplanets, yeah, if you count that, but no, the principle of uniformity says the present is the key to the past. If you see it happening now, the odds are it was happening way back in the past. And whatever happened back then is still happening now. It's not that we went through a period of major catastrophic reactions and then settled down and we're just living free and easy now. No, the same thing that we're happening now was happening then. Rocks are changed today by the same process that changed them in the past. Wearing away, that's the next chapter. Settling out, that was a couple previous chapters. Crystallizing because of heat and pressure, metamorphic, that's been happening forever. And then remelting and coming back as igneous rock. The whole process is going through. The present is the key to the past, the principle of uniformity. And this has, like I said, replaced the catastrophic models of previous thinkers. In the past, that's what we thought happened. Some big major thing that killed all the dinosaurs and stuff like this. And ever since then, we've been fat, dumb, and happy. Well, no, everything's going through the same type of things. Catastrophic events still contribute. Okay, volcanoes, earthquakes. If you're at the edge of a volcano when it erupts, that's a catastrophic event. Even though it may not be for someone a few thousand miles away, for you it is. Earthquakes, catastrophic if you're near the epicenter. Or if you on another continent, you may not even notice. Okay, meteorite impacts up in Siberia, where they had the asteroid that came down and landed not that many years ago, maybe a decade or so. pretty major, catastrophic for them. Nobody else knew it happened because Siberia is so far from anything. So yeah, they still occur, but they've always occurred. They've been occurring since the beginning. The present is the key to the past. It's not just that they occurred once and aren't going to happen again. They've been constantly going through this cycle. And here's the term. Was everybody through with the previous slide? Okay. Here's a term that follows from that. Diastrophism. Boy, they like big words in this one. Uniformity, diastrophism. The process of deformation that changes the Earth's surface. Diastrophism. Okay? We saw troph in an earlier term. Can't remember now exactly which one it was, but that means basically change. Produces structures such as plateaus, mountains, folds in the crust. This is diastrophism. Process of deformation that changes the Earth's surface. Related to volcanic activity, but doesn't have to be directly done, the movement of magma. Also related to earthquakes that can be sped up by this. But there's also just the gradual thing of bending, breaking, faulting. And that's what we're going to talk about this. The basic working theory is plate tectonics. That's what's driving this. We don't know what's driving plate tectonics, but plate tectonics seem to be driving diastrophism, constantly changing the Earth's surface, bending, folding, raising, in some senses subsiding, but not so much that. Okay? Everybody got that one? No. Okay. Later in this chapter, we're going to talk more about folding. We'll talk some about faulting. We'll talk about mountains being formed from volcanoes, but also other kinds of mountains. So there's going to be a lot of this stuff spread throughout the entire chapter. So stand by for it. It's there. Boy, am I running out of energy fast now. Of course, this is also the end of the week, so I just tend to get spent. Oh, in the text, there is a fantastic little picture there. This is 1982 image of Mount St. Helens near Seattle and Portland, in between the two, sort of. I think it's more in Oregon than it is in Washington, though. Mount St. Helens was the most notorious for its eruption May 18th, 1980. So this was taken 2 years later, the one you see in your book. We don't have a picture on the slide set. Still steaming, okay? But it blew at 8:32 a.m. when it became the deadliest and most economically destructive volcanic event in the history of the U.S. And it wasn't that major. I mean, it was big for people living nearby. There have been far bigger ones, but they usually haven't impacted that many people. This was an area that well populated. See, a lot of the activities that's gone in the past, that was not, I mean, the Indian tribes living around, that was pretty traumatic for them, but, you know, we weren't around. You know, a lot of, you know, maybe wasn't even anyone keeping a history of it. Okay. Just talking about Mount St. Helens. 57 people were killed. 250 homes were destroyed. 47 bridges destroyed. 15 miles of railways destroyed. 185 miles of highway completely destroyed. Okay? Now, do you think the eruption of a volcano builds the mountain? Would you say so? Probably. Actually, the Mount St. Helens did reduce the mountain because I think it had been extinct. That was the word for it. They're called extinct volcanoes until they're no longer extinct. Okay. Mount St. Helens continued upward before, and when it blew this time, this side facing us got blown completely off, and the magma came out and stuff, but it came out at lower places than before, so actually the mountain reduced in size a little bit because this side of the mountain blew off, and most of the magma flow, lava flow, then came down this way. It didn't make the mountain any taller at all. this is 2 years later, it's still spewing steam. So none of these things are completely extinct. They're temporarily extinct, I guess you would say. All right. All right. Everybody finished it then, right? So let's look at some of the things. Now these are two terms here that sound almost similar. They start with the same three letters, right? Stress and strain. And I think of them this way because this is just sort of how my weird mind works. Stress is the verb. That's the action. And strain is the object of the action. It's the noun, the direct object of the verb, stress. So stress is the force that tends to either, and boy, if these terms look familiar, they should be. It either compresses things, it either pulls them apart, or it deforms them. Hey, that just sounds like your plate boundaries, doesn't it? Compressive force, or what was the term we used back then? Convergent, or pulling them apart, divergent, or deforming. That would be the shear stresses, the going past each other. Okay? Same type of thing here, only on smaller scales. Three stress forces I just mentioned. They mention them here. Compressive stresses. Ooh, that sounds like it, right? The plates are moving together. So here they're talking about plates again. This is stresses. This is compressive forces. This is basically on your convergent boundaries. But it could be anywhere that you have compressive stresses. It doesn't have to be right on the major boundary. Okay, the plates are moving together, or the minor pieces of the plates are moving together. Then we have the tensional stresses where they're moving apart, and that would be like your divergent boundaries. Okay, the plates moving apart. And then the shear stresses. The plates, and again, I wouldn't use the verb sliding. I'd say moving past each other, grinding past each other. You know, these are shear stresses. These are the forces that cause the activity. Compressive stress, tensional stress, shear stress. Okay? What's the result of those? That's the strain. That's the object of the stresses. The adjustment that they make to the stresses. I left this on the board ever since. Okay? Just now noticed. Sorry about this. But you're partly right. See how it's been up there too long. We'll have to Windex and clean that. Okay. So, the strains, the adjustment to the stress. Again, three. They like Trinity something. Okay, three strain types. You can have elastic strain. Okay. Sarah, here's a volleyball player. Okay? Now, I can't remember. Did you say you were a digger? Setter. You're a setter. Okay. Sydney was the digger. Okay, all right. But when you're setting, you don't probably notice it quite as much as the other folks. But every time you hit a volleyball, especially when you're serving or something, you are stressing it. You're compressing it. And actually, if you saw the pictures, you could do this. If you can see some slow motion photographs of a player hitting a tennis ball with a tennis racket, a player hitting a baseball with a baseball bat, a player hitting a golf ball with a golf club. If you watch any of those, you'll see the ball actually flattens out. Even a baseball, golf ball, flattens out somewhere that's hitting it, and then it springs back. That's elastic. Okay? Elastic strain returns to the original shape. That's what it means, elastic. What the elastic, that you want to happen. It's not that it stretches. That's what we think elastic means. It means it returns to the original shape. Or at least we hope it does. A few things I have. Stress beyond coming back. Okay. Then we have plastic strain, and that's what I just mentioned. This is something that the event happens, but it doesn't come back. This would be A fender bender, okay? I don't know if y'all remember the old Saturn car made up in Tennessee, and their big claim to fame, one of their commercials showed the kid playing in the yard and threw a ball or hit a ball or something, and it hit the door, but the door came back. That was elastic strength, okay? But it was compared to the other cars, hit the ball on it, dent, that would be plastic strength. Molded or bent, but does not return to the original shape, okay? And then there's a fracture strength. Rather than deforming and coming back, or deforming and staying deformed, it deforms and breaks. That's a fracture strength. The rock cracks or breaks. So it doesn't just get bent and doesn't come back to the original shape. That would be the strength. That's the result. That's the object of the stress. The stress is the force, the strain is the result. The thing that happens to it. Does that kind of make sense? Okay. Now, my volleyball example. When I was in college, even in grad school, I liked playing intramural sports. I played sports in high school. I wasn't good at anything, but I enjoyed playing. And so we were on an intramural volleyball. It was a co-ed team. And we had this one really tall gal on our team that played in high school. She knew what she was doing, and I think maybe the same high school, but she had her friend who was just a great setter. And so they were the bulk of our team, but we were co-ed. But we were playing this other team that we'd never seen or something before. Got in the gym, and they had a really tall gal, and they had a really good setter with her. And we said, oh boy, this is going to be fun, isn't it? And it sure got, in volleyball you rotate sort of opposite direction, so you're always at some time, you'll be across from somebody else, okay? And it's going to rotate away so that at some point you're going to be across. And when I was across from their really good spiker, okay, I knew it was coming. It was coming every time because that setter just set her up perfectly, okay? And then, so I knew it was coming. So here, I could see it happening. And so I saw her going up. I saw the ball going up. So I went up too to give as much region to try to hit it back as I can. And I guess I got carried away and put too much into it because her spike came right into my face. I mean, and literally, volleyballs are not soft balls. I mean, yeah, they're filled with air, but they're not soft. They're pretty hard. Okay? And literally, and I'm not kidding, I felt the ball touch each ear at the same time. It deformed across my face, elastic thing. All I could see was Wilson, no, not really. I couldn't see a thing, but that made the story better. Okay, and then it bounced back, but of course it fell on my side of the net, so it didn't even go over on their side. Okay, so elastic strength. All right. Now, it almost seems like this slide should have come before the other. What are some possible material responses to the stress? Okay? One would be no change at all. You know what I'm going to do? I'm so mad I'm going to hit my fist into that concrete wall. Okay? Guess what? The wall doesn't get bothered at all by that. It doesn't make a change. My hand, of course, the bones fall apart, and yeah, it's really bad. Okay? But no change. That's a possible response to a stress. Absolutely no change at all. It either wasn't strong enough stress or it happened over a long enough time. For some reason, there was absolutely no change. Or it could have deformed temporarily, but then came back. Elastic change, recovered completely, no harm, no foul kind of stuff. Okay? Or it could have been a plastic change with no recovery. Something bent, something changed, and did not go back to the original. Or what happened to my hand when it hit the concrete wall? It broke, okay? It crushed it. It broke from the pressure and never to be the same again. Okay, I'm not going to do that, not even for y'all. Okay. What are some rock variables that would contribute to some of these various actions? Well, one is the nature of the rock, like the concrete block as opposed to my hand. The block's not going to change, my hand is, okay? So, the nature of the rock. Well, let's get a little more serious. Sandstone is probably going to change more rapidly than granite, because granite is igneous rock, sandstone is just sedimentary rock. However, metamorphic rock may be more resistant to change than even igneous rock, because that's undergone pressure, temperature, change of the crystal structure. Okay? So the nature of the rock. How heavy is it? How hard is it? Is it mostly iron? Is it, got lots of silver? Yeah. The nature of the rock. Okay? That's one rock variable. But here, to me, is the bigger one. The temperature of the rock. Okay? Now, trying to think of a good example of this. There's lots that are okay, but I can't think of anyone. But anytime you heat something up, it's going to be more likely to deform. Okay? Go to one of the steel mills. They heat that rock, the steel to really high temperature. They can roll it, they can melt, they can do all sorts of things to it when it's hot. When it's cooled, sort of hard to change. That's like the concrete block wall there. Okay? So the temperature of the rock is going to contribute to whether, if it's hard, cold rock, then probably it's going to have no change or elastic change for the recovery. If it's a very warm rock, it could easily deform and not come back. Okay? The speed of the stress application. I mentioned this in an earlier thing. Did it happen suddenly, or did it happen slowly over time? Okay? I could easily see slowly over time either no change or elastic change. But if it was also hot, that slow over time could create a plastic change. You don't even notice it is changing, but it does. Okay? Or a very rapid stress application, either nothing happens or you might actually break it. Okay? So you could have either extreme there. Okay? Or it could be elastic or whatever. Okay? The speed of the stress application. And then the other would be the confining pressure. How deep is this happening? How far below the surface is it so that, even though you have something happening, it's being held in place so tightly, maybe there will be no change. Okay? So the confining pressure might also contribute to which of these is happening. Or if that confining pressure is uneven, like getting here late, that would be a contributing factor. Just under the wire or over the wire or next to the wire or something. Okay. Has anyone else come in since I finished calling roll?
I should be the last person.
What's that?
1, 2, 3, 4. Yeah, I'm the last.
I can tell you the last one who has come in. I've witnessed that one. Okay. Here's the other issue here. What if the confining pressure is uneven? Maybe there's a lot of pressure on the underneath side, but less on the top side. That could form a plastic change. Because, especially if there's heat involved, it's going to be molded this way. And that isn't going to bounce back. That won't be elastic. Okay? That won't be no change either. Okay? So it could be the confining pressure. Okay. And we'll see some examples of that a little bit later too. Okay, the interplay of all these things, okay, especially the rock variables, but also with the other things here, that's observed in the rock structure, okay? And you can, and I highly recommend you do this, drive down the highway where there's been road cuts. You see these, especially going up toward Huntsville. They're cut right through a steep hillside. And you can see sometimes the rocks are like this, sometimes they're flat, sometimes they're like this. I drive my wife crazy, fascinated at the various things you see here. I say, what you reckon causes that? Who cares? You know, is the typical response. But, you know, it's pretty interesting to think about. Okay? Here is sort of a classic illustration of elastic and plastic and rupture. Okay? From the previous slide that we covered. Okay? Anytime, and this is sort of backwards to me. To me, I always put the driving force on the horizontal axis, the independent variable there, and the resulting thing on the vertical axis. This has them reversed, and I guess there's a reason for it, but I don't know what it is. They have the stress on the vertical axis and the strain here, the action and the reaction here. I usually think of it being otherwise. If you exert a stress on A, and you're increasing the stress, the strain, stress is this way, strain is this way. So you exert this much stress, you get this much strain. A lot of stress, and going up, okay? Now, as long as they are equivalent, or the ratio to stress to strain you might think of as being somewhat constant, then you're going to get linear reaction. And that is elastic. That's usually elastic reaction. Okay? Here's object A, exert a certain stress, and it changes a little bit. Object B, it changes a lot more. Okay? Now, they don't always have to follow this pattern, but they could be. One material might resist change altogether. Others might react somewhat, others might react a lot. Okay? But as long as it's a linear reaction, that's elastic behavior. Anytime it's close to a straight line. However, once you get some bending going there, that's the limit of your elastic behavior somewhere up here. I would end it right here. And that's when you start having plastic deformation. It's not coming back. You add more stress, and it actually warps it even more. Okay? Now, just about any rock, if you add enough stress, it's going to rupture. It could be at the end of elastic, it could be at the end of plastic. Either one, but at some point it's going to rupture. And again, it wouldn't just be the stress, it could be the speed of the stress. I can easily imagine a very slow pressure on something, deforming it, bending it. You know, it might come back or not, but if you do the same force but do it real quickly, actually fracturing it. You can do that with glass. You can push on it very gently, and push and push and push, so you're doing a pretty, or you can just tap on it real quickly with not as much force as you were pushing and actually crack the glass. So that's the kind of thing. Rupture could occur just about any time. Okay? So, and usually the plastic, to me, depends a lot on temperature. Okay? You can change everything with a change of temperature. All right. Now let's talk about rocks and specifically mountains. Okay? Yeah, I think we'll be okay. What we're dealing with here is mostly sedimentary rock. Mostly sedimentary rock. And there's a reason for this. With sedimentary rock, usually it settles out in flat layers. I mean, by the definition of settling, you're going to be in flat layers. This thing settles, that thing settles, that thing settles. Igneous rock can be formed three-dimensionally any way you want to. Sedimentary rocks in layers. Okay? Metamorphic rock. You know, all sorts of things could have happened to that metamorphic rock with all those additional, and it's going to deform. But sedimentary rocks originally are flat sedimentary deposits. Okay? The layers are usually horizontal. Now, I can't remember. No, it's coming up next chapter. We'll see some incredible pictures of the Grand Canyon. Have any of you ever been out there?
I never.
Okay.
I was at the Grand Canyon.
Right. Didn't you notice that just about all the layers are flat?
Well, I couldn't quite notice that because I was like 11.
Oh, I see. Okay.
Because, I mean, We was only there, me and my mom and stepdad. I mean, we was only there for about maybe an hour. So
Yeah.
I couldn't tell because I was just a kid.
Yeah, right. I almost wanted to kick myself because when I entered the Navy, I had to drive across country to San Francisco to catch my flight to go to my first ship. Well, I was so afraid that I wouldn't get there in time and stuff like this. I drove right past the exit off the interstate, and the Grand Canyon couldn't have been more than, say, 40 or 50 miles away. But I just couldn't risk it because, what if a car broke down or something like that? I couldn't afford to miss my flight to my first ship. And then when I was coming back, I was having car problems, okay? I let a friend of mine use my car when I had been last deployed, and when I came back, it wasn't running quite right, and finally I found out what it was. It was just heating. The cooling system was completely messed up.
What did to your car?
So already I was running behind, and I had planned to stop and see the Grand Canyon, if only for an hour or two, but I was running like a day behind by this point. I thought I can't afford because I had another duty station to go to, so I didn't want to risk missing that. So I drove right past the Grand Canyon, not within sight, but close enough I should have stopped, and I haven't seen it since. But when we see the pictures, you'll see sedimentary rock were all in layers. Okay. So what we're talking about here, folding, is when you see what used to be layers and they're no longer layers. There are bends in that layered bedrock. You think, what caused that? Well, that process is called folding. As a result of a stress-produced plastic strain. If it didn't do an elastic strain, that would have come back. It was slow over time and maybe with heat involved and bent it, and it didn't come back. Like the car, the ball into the side of the car, and it didn't pop back out. Okay, plastic strain. Widespread horizontal stress can produce domes or basins. So horizontal stresses, you could produce a dome, forcing it up, sort of like the Himalayan mountains were forced up when two plates collided. Or, if it was a spreading type thing, it could produce a basin. Okay? Now, I guess the stresses could form from a variety of ways. I was in soil science when I was in grad school, and there was a type, and we had them on the farm. I never knew what they were called. Things called grady ponds. They were things that in wet weather they held water, but when it got real dry, they didn't. So they were not a permanent pond or a permanent lake or something like that. They were called a grady pond. And I found out the reason for them is that the underlying material was a chalk that actually interacted, a chalk type material that when it mixed with an acid, then it gave off carbon dioxide. It basically,
It sunk down.
yeah, it just sort of disappeared.
Decompressed.
Yeah. And that's called a grady pond in those low-lying areas. Usually that's where you'll find swamps and things like this. Or not, you're just riding along, suddenly there's a low-lying area. More than likely that's a grady pond. Well, that would be more like a basin. Something gave way underneath, and you wound up with a fold in if you had bedrock. Now, there's two structures that could be. Now, these are the basins and the domes. Those are sort of three-dimensional. If they're two-dimensional, the anticline is the arch-shaped structure, like this. The forces did them up like this. The syncline was the trough-shaped structure like this. Here's how I remember. Anti-arch, beginning with A, anticline, arch. Syncline, I don't have anything, so that's just the other one, trough-shaped. Okay? So here's the illustrations of that. That would be which? Anticline or syncline? That would be anticline, the arch. The forces up here have been pushing upward the younger strata on top, and they are bent like this. That is the anticline. They don't label it here, but that's what it is. Whereas this would be a, help me, It's not an anticline, let's say. Syncline, that would be your syncline. Here, something's given away at the bottom, and it's folded and permanently deformed. Now notice these were originally horizontal stratified rock, okay, sedimentary rock. Now it's been bent upward or bent, oh, too many. Bent, oh, where is it? There it is. Bent downward. Something gave way. Something like lost soil underneath. A sinkhole would sort of be like this. Something is worn out, you have something to eat.
It's like a dig in the earth. Basically.
Yes, yeah, exactly. Okay? So this would be your syncline. The younger strata is down low now, older strata even lower. Okay, that's an example of folding rock. Okay? Now, it's time, isn't it? Yuck, I should have paused otherwise. Okay.
3:15.
Yeah, that's what I said. We've run out of time. I probably shouldn't have started this. We'll do folding right here. I don't know what slide that is, but some slide in there. Okay.
Let me check see what slide it is. Hang on.
What's that?
Let me check see what slide it is. Hang on.
Okay. I think when I close it out, I can see that too. Let me see if that works. Slide 8.
Slide 8.
8 of 26. So, slide 8. Okay. All right, and we'll pick up there next time. All right. So we didn't get super far into the new chapter, but we did get a decent start. Okay. Now, I think what I'll do, I'm going to pause my... Okay, someone remind me, tell me, what was the mass of the basalt?
The mass of the basalt.
The mass of the basalt is 161.
Second?
161.
161 grams.
Yeah.
What was the volume of the basalt? 48 cubic centimeters. What was the mass? Someone did the calculation? 3.35 grams per cubic centimeter. Okay, that was the density of basalt. Divide the mass by the volume. Then the mass of the granite?
447 grams.
447?
Yeah.
47 grams. And what was the the volume of the?
188 cubic centimeters.
Okay, 188 cubic centimeters. Okay, and then when you did the division, what did you get?
2.37 grams per cubic centimeter.
Okay, 2.37 grams per cubic centimeter. Now I want to remind you of something, and that's something we saw in the book. And I think at the time I said, remember this table, okay? Let's see if I can find it again. Last time I could not find it to save myself at all. So let me see if I can find it again. And let's see how well we did. Okay? Yeah, here we go. If you find in your text, table 18.1 on page 461, you'll see comparison of oceanic crust, which is made mostly of
Water.
crust. Crust. Basalt, you're absolutely right. As opposed to continental crust, which is made mostly of granite. The density of the oceanic crust, right around 3.0 grams per cubic centimeter. What do we get? 3.35, not far, right? Huh? No. I'm reading from this, and then your results from the last page. And the granite, and this it says about 2.7 grams per cubic centimeter. What did y'all get? 2.4, and without the spillage, we might have gotten up to 2.5 or 6. I mean, down to, I'm sorry. Yeah, up to 2.5 or 6. So we would have been pretty close there too. So just to show you, we did get really close to what they said. Okay, Now let's turn to the questions. Okay? The two of them are on page 336 and two on 337. Okay? In what ways do igneous rocks have different properties? Yes. Density is one. Say again. Okay, volume and mass are not really properties, but density is. Say again. Color, for sure. And you notice the color change here. Say again. Luster. Yeah, we didn't do much with luster here, but that is a property. Others? Huh? Okay, location, that probably not. Say again? Okay, and that kind of stuff too. We didn't really do much with that in this lab, but yeah, you're right on the money. In what ways do igneous rocks have different properties? The color and density are two big ones. There's also the mineral content. The what?
The scale of the hardness.
Yeah, okay, there's that too, though we didn't do anything with that today either. But we did see evidence of mineral content, right? Some were higher in iron, some lower in iron. Okay. So, number 2, explain the theoretical process or processes responsible for producing the different properties in igneous rock. Yes.
How fast it cool down?
Okay, that would be crystal size, and we didn't mention them. So up top, one of the different properties are crystal size or texture. Either one of those words would work. And the speed of cooling determines crystal size. And we did notice that in our rocks today, which was which? We did notice crystal size in our rocks today. The granite is which?
The land.
The what?
The land. Continental.
Are you asking like it cooled faster or what?
Yeah, it cooled faster or slower?
Slower.
Slower, and what was the result? What can you see in the granite?
The bigger.
Larger crystal size, exactly. Coarser texture on those rough areas. Okay? So there's one theoretical process for producing the different property. The different size crystals or texture, that came from cooling rate. Very good. How about color?
The
iron
location.
level in it.
The what? Iron content, exactly. Iron content, that would be one. How about density? Same type thing. Iron content again. Okay, because iron is heavy. What's that?
Do location matter? Like in what you're talking about? How different areas of the earth got different
Okay,
types of soil?
in a sense, okay, now that you mention that, granite usually comes from the continental crust, whereas basalt comes from the oceanic crust. So in that sense, I would say location may be a contributor. Okay? That all right for number 2? Okay. Number 3, according to the experimental evidence that you measured, okay, propose an explanation for the observation that the bulk of the Earth's continents are granite, where the bulk of the basalts are found mostly in the Earth's interior. What's that? Yeah, the lighter weight continental crust would be kind of floating on the denser oceanic crust. So there is one way to express it.
Wait, say that again.
Okay? The lighter weight continental crust would, in a sense, float higher on the asthenosphere than the denser oceanic crust,
So
where the
basically,
basalts
the
are.
lighter elements will float in the
Well, yeah, will rise and the denser ones will fall. Exactly.
Wait, you said the lighter weight of.
The lighter weighted or density, lower density granite is in the continental crust, and it goes up compared to the denser basalt in the oceanic crust moving downward. All right. Now, all of you answer number 4 however you want to. Okay? That's up to you. That's your interpretation. I need an answer. If there's no answer there, you don't get credit. But if you put an answer yes or no, why or why not, whatever, you get credit for that question. But that only gives us 6 questions on the back, 6 blanks on the back, 4 on the questions. That's only 10 points. We need 25. So what we do for here, the other 15 or more points, if you go to your book, and this is what I said, remember this at the end of the chapter, chapter 18, on page 478 in the current edition, okay, at the top of the page are questions for thought, okay, 16 of them. Then there's, for further analysis, 4. So those added together give you 20. You can choose any 15 or more of these 20 questions and answer those. That will be the other 15 points on your lab.
What chapter?
This is chapter 18.
On the book, on this book, we have 15 questions for thought and 4 further analysis.
Okay, which chapter is this?
18.
Okay. Yeah, it's the same.
Questions for thought?
Okay, there's questions for thought, 16. For further analysis, 4. That's a total of 20. Do any 15 or more of those 20 questions. Write them on a piece of paper. I don't think you have room on this lab because there's only half a page available there. So write them on a piece of paper and turn them in. Now, okay, are y'all listening? Okay. You don't have to write the question, but so I can tell which one it is, do QFT for questions for thought, FFA for further analysis, okay? Especially in 1 through 4, because those are the same numbers. The QFTs for 5 through 16, those are the only ones with those numbers. But for 1 through 4, we put QFT for questions for thought, or FFA for further analysis. Say that one more time. I can't hear you.
This is what we're doing for the rest.
Yes, yes,
No,
exactly.
we do it here, not at home.
You can, or you can do it either place you want to. Okay? Here's a suggestion, and a very strong suggestion. Witness over time, many terms teaching this course. Okay? The lab technically isn't due until a week from today. That would be next Thursday, right? However, your test on this chapter is next Tuesday. So I recommend, strongly recommend, you do these answers before the test on Tuesday, because that's going to help you study for the test. Now I've had, yes?
Can we use the questions as like study guide or help test like we did in the first test?
Okay, yeah. Every test you can have anything you want to write on a piece of paper and bring with you during the test. Okay? So, does everybody, say again?
Did you do the, are you going to do the lab call thing? The row or whatever?
Oh, is it time? It probably is, isn't it? Okay. It sounds like somebody.
I got 358.
Huh?
You have to go to this page in your textbook, the end of chapter 18, and do
15 plus the 4.
okay, you can do questions for thought 1 through 16, and then further analysis 1 through 4. So that's
Kiara
4
never
questions.
made
You
it
can
in
pick 15.
today.
To answer, you have to answer
Matt is
just
still
15,
here.
but you can answer more. if you
Curious
want.
board
I've
we've never
actually-
seen.
15 or more, just get one.
Dante's
Yeah,
still
15 or
here.
more. You have to do at least 15.
Okay.
Yeah,
Okay.
and it's the
I
end of
is
chapter
still
18.
here.
So it's the chapter
Demetrius is
18.
still here. And Destiny is still here. Justin's still here. Demetrius is still here. Ishmael is still here. Aaron's still here. Zachary's still here. David's never made it in today. Sarah's still here. Max is still here. Yandra is still here.
Oh, I don't know what you're talking about.
I may have.
No, this is it. You're having you look at it. It's a thing. It's a thing.
4, 7,
Looks like you're like attacking.
12, 13, 14. as long as you put for the first 4, which question set it came out of, and then for the rest of them, I don't care. You can do them any order you want to. You need at least 15 questions. Now, why did I say 15 or more? Well, not extra credit, but to make sure you get up to 25 points. What if you miss a question? Well, if you do an extra one and get the next one right, then you get your 25 points. But if you didn't get the question, then you might only wind up with 24 or 23 or 22. So, yeah. So, we do have a test today on chapter 17.
That's at 5.
That's gonna be
coming out this day.
What's that?
I said that's the last 30 minutes of class coming out.
Yeah. But if you finish your questions before then, you can start taking your test early. Do you want to move back to the classroom, or are you comfortable on these stools?
I mean, I'm good over here because I got elbows.
Okay? You'd rather work here.
While on the desk sitting there, no way.
And this is a lab, so you can work together. But everybody will need to turn in his answers and her answers, not a team answer. Okay. All right. So, I'm going to, do you think there's any reason to keep the screencast-o-matic going? I'm going to end this.